to this. Okay, welcome back, everybody. It's Wednesday. We're going to continue on with chapter 8, which is reactions of alkenes. Remember, this is the part where I'm starting to get really excited. It's talking real chemistry. We're starting to really make things and have to plan out ahead and say, ooh, if I want this product, what kind of starting material do I have to start with? And so this is where we're going to start to see, the chemistry, all of those basics we've done up to now are coming together. Okay, for administration, we have modulate homework is due Friday at midnight. And so that we want to have all those stuff in. We have class today, and on Friday, we have class also. We're going to talk about reactions of alkynes. Okay, so before we begin, I want to go ahead and let Nicholas go ahead and give a few comments about the SI sessions, and then we will move on to our lecture.
Thank you. So I only really have a couple comments. The first is that there are 2 more sessions that you can make to get credit for the course. Thursday and Friday are my last 2 sessions that you can get credit for to improve your participation grade. And then sessions will continue after that. It's just it won't count towards like your grade. The second announcement is it's like a recruitment announcement. If you are doing well in the course, you enjoy organic chemistry, you're moving on to organic chemistry 2, the SI program is looking for new SIs. I love this job. It is making me much more comfortable when thinking about taking the MCAT next spring. Just having this reinforcement of taking the course twice has been really huge in filling those gaps that I have in my learning for organic chemistry the first time around. So if you want to improve your resume, you want to get better at organic chemistry while you're taking OChem 2, definitely consider applying to be an SI. You can find all that information. I'll put the link in the chat, but let's go ahead and get started with class. Thank you.
So, and I mean, he said you don't have to keep coming, but you should, because it's not for a grade, additional grade in your class, but it is shown to improve your grade. Every test after this, every SI session you go to is shown to add points to your test grade. So please continue to go. And those of you who have gone every time, I bet you've seen that you learn something new every single time you go, or it's solidified or it's reinforced. So I highly recommend you continuing going on and doing that. Okay, if there are no questions, I'm going to go ahead and pull up my slides. You can type your questions in the chat or just go ahead and see if you can talk. I'm going to go ahead and share my slides again.
Dr. Irvin?
Yes.
Are you not going to teach Organic Chemistry 2 next semester?
I am not teaching Organic Chemistry 2, but Dr. Vincent Guerra, Brittany Vincent Guerra, uses Top Hat, and she has taught this 2 times using Top Hat. And so if you want to follow on this exact formula, I would suggest going ahead and taking her class.
All right, thank you.
Okay, so yeah, that goes for everybody. If you like Top Hat, if you liked it better than taking anything on Examity, if you think the interactive homework is better than the book homework, I highly recommend you go ahead and sign up for Dr. B's class. And we worked on this together over the summer to rearrange the book so it follows Solomon, so everybody's learning the same information. We just thought there were so many cool things associated with the homework, associated with the 3D modeling tools, associated with the testing, that we thought this was a great opportunity for us to use this in our online teaching. Okay, why isn't it sharing? Okay, connected. All right, hang on. For some reason, it's not letting me share. I've trusted it before. When prompted, okay. Why isn't it sharing? Okay, let me try to unplug it and plug it back in. And yeah, there it goes. Just goes to show you just gotta plug it in and it'll work. Okay, alkenes. All right, I'm gonna move this over just a little bit on my screen. Okay, hopefully everybody sees our alkenes here. Now, the last thing we talked about was we looked at the review that we'll have at the end of this one too, that each of these reactions we've shown has a regiospecificity. Yeah, thank you, Vincent Guerra. I don't say it correctly, I apologize. But and Dr. Allison teaches out of the that uses Sapling and the Solomon's book. So, okay, all right. So we learned that the reactions have regioselectivity, meaning that if you're adding an acid or water across a double bond, the hydrogen's going to go to the side with the more hydrogens, and that's called Markovnikov's rule. And then when we looked at our adding halogens across there, we saw that it had an intermediate that required an anti-addition. The other nucleophile had to come in and open that ring on the bottom side. So the regiospecificity of where these things add is important, okay? So in the first two, we had what we did was Markovnikov's rule. The hydrogen was on the more hydrogen substituted side. Okay, now we're going to do something that seems to break the rule, but it follows some other rules too. Okay, so in the case of this, we have what we call hydroboration oxidation of alkenes. So the first step is where we take a boron and a hydrogen, or a borane type compound. We're going to add it across the double bond. Okay, and we're going to add it across the double bond at the same time, so that the hydrogen and boron attach at the same time, so there's no rearrangements. But then there's a second step of the reaction. The second step of the reaction is actually taking peroxide and oxidizing the carbon boron bond to give us our alcohol at the end. So just like in the creation of the hydration of an alkene, we now have another way to generate an alcohol. But it's going to put the alcohol on the least substituted side, which is the opposite of hydration, where it always puts it on the more substituted side. Okay, so that specificity is very important to keep track of in our next little section here. Okay, so the idea here is that we have a boron type complex. And in this case, the simplest way to look at it is the boron with 3 hydrogens on it. Although that itself is not stable, we actually use other things to make it happen. And what we'll see is that the hydrogen is going to go on the more substituted side, and the boron's going to go on the least substituted side. Now, it's going to keep doing that reaction until all those boron-hydrogen bonds are gone. So what you actually end up doing is making a really big, huge molecule with all centered around that boron. Okay. Then the next step is we're going to oxidize these boron-carbon bonds to give us alcohols on those carbons. Okay, and then we also end up with a borate of the sodium salt of boric acid at the end as well. Okay, so what we can do now, let's go ahead and look at that in a little more detail. So most commonly when we do this, we have some kind of reagent. And notice that in this case, we're using a di-substituted alkene on this side, and there's just hydrogens on this side. When we do this, there's a couple different components. There's an electronic component and there's a steric component in every reaction. So we need to pay attention to that in how we add this over. So again, we can use 3 equivalents of our alkene for every 1 equivalent of our boron compound, because it does make that tri-alkyl boron intermediate. And then when we finally oxidize it off, we get our alcohol here. Note, this is very different than in our dilute sulfuric acid. We have sulfuric acid, but we have a lot of water, so it'll hydrate. In the case of that, this is our intermediate. This boron complex is our intermediate. Those are sigma bonds between the boron and the carbon. Okay, so it's a nice, stable, isolatable material. In our using our dilute sulfuric acid, which has water in it, we actually form that carbocation, and then the water acts as a weak nucleophile. Therefore, we have to always form the more stable carbocation. And in that case, it gives us our hydrogen on the more hydrogenated side. And that means that our oxygen, our alcohol at the end is going to be on the more substituted carbon. Notice that's completely opposite of the boron. In the case of the boron, the oxygen is going to be on the least substituted carbon. Okay. So what that means is the net reaction is when we do this right here, we end up with getting primary alcohols. Okay. When we had the sulfuric acid, we could only get secondary and tertiary alcohols from that system. Okay. We could never get a primary alcohol. So this gives us an opportunity to get a primary alcohol. And if there was a choice between a primary and a secondary alcohol in the sulfuric acid system, you always got the tertiary alcohol. I'm sorry. If there was a choice between a secondary and a tertiary alcohol, you always got the tertiary alcohol. Okay. So that would look more like this right here. Okay. So that regiospecificity is something you need to pay attention to. Okay. Now, the reason we have this stereospecific reaction is partly to do with the idea that the boron and the hydrogen add across the same side of the double bond. Okay. And when they add across the same side of the double bond, it creates a sigma bond between the boron there, and the hydrogen created its sigma bond also. Okay. Now, when we oxidize it off, it doesn't go through, it's not a substitution reaction, it's an insertion reaction. We're actually inserting oxygen into that bond. And so wherever the boron was, whatever the stereochemistry the boron had, you maintain that stereochemistry in the alcohol produced. Okay. So when you have that, so that's a very different thing. That's the really cool thing about these boron reactions is number one, it's the least substituted carbon where the boron goes, and the oxygen has the exact same stereochemistry as the boron had. Okay, so let's kind of figure out why. Okay, so if we look at boron, it kind of looks like a carbocation. It's one of those weird ones that can only have, that is stable at 6 valence electrons. And so it actually is a trigonal planar, and it has this empty p orbital. Okay, that looks a lot like a carbocation. But because boron has a filled s orbital, it actually has no charge. I mean, sorry, it has a filled p orbital, it has no charge. Okay, so, but because it doesn't have that full octet, it actually isn't very stable, and so it dimerizes immediately and forms this compound here, which is can be used in the reaction, and that's fine. Or you can trick it into forming a complex like this. And so most of the time we'll see the BH3.THF. Okay, that's this tetrahydrofuran, which we usually use as a solvent. It's a nice ether, but it also forms nice complexes with these Lewis acids. And so what we'll see here is that this is the most common reagent used for this right here, BH3.THF. So it's a borane tetrahydrofuran complex. Okay. So the mechanism is believed to be a concerted reaction. Remember, a concerted reaction is where it adds all at the same time. So when we look at how that happens, that's why the hydrogen and the boron add to the same side of the double bond, because it's a concerted reaction. Okay, so we have this empty p orbital of the boron right here coming in and interacting with this electron-rich pi orbital, and it starts to interact and starts to form this transition state, this square transition state here, and then it finally gives us our product here. Okay, that formation of that transition state and the electronics of that formation state and the sterics of that transition state control how it adds on that double bond. Okay, so let's first look at the electronic factor of this. Okay, boron is electron poor. It has a lower electron affinity than the hydrogen does. But as it forms this complex, it becomes partially negative. And as our double bond of our alkene starts to break, we're going to see the side that's more substituted being partially positive. Okay. So when we have that transition state form, we have this nice Lewis acid base addition and alignment to give us our boron on our least substituted carbon. So that's the electronic factor. Okay. And if we think about it here, the boron is the less electronegative atom. When we added HCl across the double bond, hydrogen was the less electronegative atom. When we added the water across that double bond, the hydrogen was the less electronegative atom. So it follows the rule, that electronic factor, that the boron is going to go, because it's the less electronegative atom, it's going to go on the one that has the least number of substitutions. Okay. The second factor we have is sterics. Okay. So if we have a disubstituted alkene here, and when we try to form that transition state, we're going to have these hydrogens be butted up right against those methyl groups. Okay, so we're starting to see a steric repulsion for that system to create that product, right? So if we have that transition state, it's going to be higher in energy than if we did the transition state the other way. Notice here we have a hydrogen that's not butting up against these, and these hydrogens are only butting up against hydrogens. That has less of a steric demand, making this transition state lower in energy, making it faster, right? Any transition state that's lower in energy is faster, therefore this becomes our major product. So this is the steric argument on why this borane addition, this addition is anti-Markovnikov, or adds to the least substituted carbon. And the electronic argument works well too, with the idea that it's the least electronegative atom. Okay. So that's the steric effect. All right. So that's just how we add the boron on there. Remember, that's a stable sigma bond. Okay. So now that we have that added on there, we need to break it off to get us to our alcohol. And the way we do that is we use an oxidizing agent called peroxide. Now, this is just an oxygen added to water, so it has an extra oxygen, and it wants to get rid of that oxygen. And so when we take that water-like substance and put it with a base, it's going to deprotonate that to give us our hypoperoxide ion. Okay, so imagine we have a good nucleophile here, we have an extra little oxygen there, and what's going to happen is the nucleophile is going to attack that boron center, because the boron is the most electropositive atom in the group there because of that empty p orbital. Okay, so it's going to attack that empty p orbital and create a new sigma bond, but now it has more electrons than it needs, and we have a negative charge on boron. Okay, so that's going to rearrange. We're going to lose those, and it's going to transfer. Let me change colors here so you can see this real quick. We're going to transfer the electrons from this bond, this sigma bond with carbon, to the oxygen. Okay, so see what we're doing? We're taking that negative charge on boron, we're taking those 2 electrons that are in that sigma bond, and moving them to oxygen to get back to our neutral species. Okay, and in the process, we lose these 2 electrons to regenerate our hydroxide ion. So now we've gone from our neutral species with an empty p orbital back to a neutral species with an empty p orbital, which means it can happen 2 more times. Each of those carbon boron bonds is going to be reacted with the hydroperoxide ion to keep breaking them off again and again until all you have is your alcohol and the salt of boric acid, sodium 3 boron oxygen 3. Okay, so do we see why the boron adds at the least substituted carbon? And do we see that the next step is an oxidation on that boron And because it's doing an insertion in that bond, we retain stereochemistry. All right. So because we're migrating that carbon, we're not forming a carbocation, we're not doing anything else, we retain that stereochemistry. It's just transferring over to the oxygen so the boron can lose that negative charge. Okay. The hydroboration oxidation is considered a syn addition because it's adding the hydrogen and the boron to the same side of the double bond, but it's anti-Markovnikov because the boron ends up on the least substituted center. And the next step replaces that boron with a hydroxyl group. But again, it replaces that hydroxyl group without a carbocation and without rearrangement, giving us the same stereochemistry and regiochemistry we had where the boron was. So it's a nice straightforward reaction with no tricks up its sleeve. Okay, so that's boron. So that's hydroboration oxidation. Okay, let's do that again with a different species. And in this case, we're going to use mercury. Okay, obviously mercury has some toxicity issues, but it has a certain regioselectivity that the boron and the other reactions don't have. Okay, so the regioselectivity is why we use this mercury reagent. Okay, so we do what we call an oxymercurization, which means we're going to add mercury and a hydroxide to a double bond. And then the second step is removing the mercury by a reduction step. Okay, so it's actually two things are happening. The first step, just like the hydroboration oxidation, is 2 steps. Oxymercurization, demercurization is 2 steps. So the first thing we're going to do with this is we're going to take mercury 2, which is +2, and we're going to, in the presence of water, add it across a double bond. When we do that, we're going to get our mercury on our least substituted atom, basically our anti-Markovnikov addition, right? Okay, so the mercury is going to add exactly where the boron would have added. However, because we have water here, the water is going to end up on the more substituted carbon. Okay, so the net result is the oxygen is adding in a Markovnikov fashion. The oxygen is going to be on the more substituted carbon. Okay, because we're using the mercury to direct the reaction. Okay, so didn't we already do this with sulfuric acid and water when we did the hydration? Kinda, but that went through a carbocation. So there was a possibility for rearrangement. Let's see why this one's different. Okay, so in the case of this, we have our mercury, which is has a positive charge on it because in the neutral salt here, it's has a mercury +2, and when we lose one of the acetate ions right here, we now have a mercury +1. So now we have an electrophile. Okay, and we have an alkene. Our alkene is a nucleophile. So now we have a nucleophilic electrophilic reaction. Okay, so the next thing that can happen is we can have our electrophile come in and attack our nucleophile, and then we form an interesting transition state here. Okay, so we can form our carbocation on our more substituted carbon here, or we can have it do a bridge structure. Okay, now remember we had that same 3-membered ring bridge structure when we did the halogenation of that double bond. Okay, so now because that ring structure is slightly more stable, it's going to be that in that system. Unlike in the boron system, it's not symmetrical. Okay, and if we look at why that's not symmetrical, so notice that in this case here, in this first step here, that first, carbon is carrying the full positive charge. Okay, so that's, you know, we've done that. We can do that. In this second version here, mercury is carrying that full positive charge. Okay, so mercury likes to be an ion, and so that's why this particular configuration is the more stable, because everybody has a full octet. Okay, so, but unlike boron, it's not symmetrical. Because we have that positive charge on mercury here, we actually have a longer bond, a weaker bond to the more substituted carbon, because that more substituted carbon can carry that partially positive charge. Okay, think of it as that partially positive charge is always more stable, you know, just like a carbocation would be. Okay, so that being said, our mercury adds to one side of the reaction. It forms a 3-member transition state. What does that mean about where the water has to add? In our three-member transition state here, our other halogen had to add from the bottom, right? So what we see here is that when we do that, we have the same thing happen. As you form this 3-member transition state, even though it's not symmetrical as it was in boron, the hydroxide ion, or the water in this case, has to come in from the opposite direction. So it has to come an anti-addition, okay? Just like we saw in the halogenation of the alkene because of that 3-member transition state. Now, because it's not symmetrical, the hydroxide's gonna go on the more substituted carbon. Okay, so it's always gonna go on the tertiary or the secondary if that's the highest value we have. All right, so then the next step is the demercurization. And in the demercurization, that's just removal of the mercury by the addition of a hydrogen to that position, okay? So in this case, we're gonna use a boron containing reducing agent called sodium borohydride, okay? So in this case here, we have a boron with a negative charge on it because of the extra electrons with the hydrogen. And so it's going to transfer a hydrogen and its electrons to the place where the mercury was, giving us our new carbon hydrogen sigma bond. Okay, and most of the time it really doesn't matter because this half of the molecule usually isn't chiral. However, this half of the molecule can be chiral, so we don't have to worry about that. Now, because it's going through this radical mechanism, we don't really know which the specificity is. I think somebody probably figured it out, but I don't know. Okay. The reason we do this mercurization, demercurization, is that because of that formation of the 3-member transition state, you do not have carbocation rearrangements. Remember, when we did this right here with the dilute sulfuric acid, we formed a carbocation, and if it could find a more stable carbocation, it would rearrange and give us that more substituted alcohol. Okay. In the case of the mercurization, demercurization, we do not have a carbocation forming, therefore we have no carbocation rearrangement, meaning we can be very selective about where our OH goes. Okay, so what does that mean? Okay, all right. All right, well, let me compare the hydroboration versus the mercurization. In the case of the hydroboration oxidation reaction, we can easily form primary alcohols, because if we have a terminal alkene, we're going to add the boron to the least substituted carbon, and when we oxidize it off, we get a primary alcohol. Okay, if we do oxymercurization, demercurization on that same alkene, the mercury is going to add to the least substituted carbon, making our second carbon over have the alcohol in it, giving us a secondary alcohol. So boron here, this is the only way for us to form a primary alcohol doing the steps we have right now. And this gives us selectivity where it doesn't rearrange to give us anything other than the alcohol on one of those 2 carbons of the alkene. Okay, so that's the key here, is selectivity about where the hydroxide ends up. Okay, so to sum up all of those together, if we just took our sulfuric acid and water, it's going to form a carbocation, it's going to rearrange, it's going to move around and give us the most substituted alcohol. And oh, darn it. Where is it? Where is it? There it is. All right. It's going to rearrange, forming that carbocation, giving us our tertiary alcohol. And if it can form that tertiary alcohol, it will rearrange until it does. Okay. Now, in the mercurization, demercurization reaction here, the alcohol shows up on the most substituted alkene, but does not rearrange. Okay. So we end up with our secondary alcohol. And in our boron reaction, our boronation oxidation reaction, we end up with the boron on the least substituted part, and therefore we get the boron on the least substituted part of the alkene, which gives us a primary alcohol. So, same substrate, choose your reaction to choose what your product is. Okay, so this needs to be written down on a table somewhere. You know, show yourself that you can choose your product based on which reaction you choose to run. Okay, so questions on that. So those last 3 reactions, those last reactions there are all about selectively putting your alcohol exactly where you want it. Okay. All right, so now we're going to move on to something a little bit different. We're going to look at another thing we can do to an alkene. And in this case, we're going to add an oxygen across that alkene to form a cyclic ether called an epoxide. Okay, it's called oxycyclopropane because it's got 3 members of the ring. So it's propane, but it's got an oxygen in it. So it's oxycyclopropane. Okay, so these are very useful. And in fact, when we go to chapter 11, by the end of the year, we're going to talk about a lot of reactions these things do. But right here, we're going to talk about how to make them because it's an addition of an oxygen across a double bond. So we have our double bond and we're going to add an oxygen to it. Now, in all of these reactions, we use what we call a peroxide. A peroxide is a reagent that has an extra oxygen in it. So for example, if you had acetic acid, and you added an extra oxygen to it, you would have peroxyacetic acid, or in this case, peroxyethanoic acid. Yeah, you can name. One of the really common reagents is called MCPBA. Whoa, come back. MCPBA means metachloroperbenzoic acid. So if you look at here, you got a chloride here, and then this is benzoic acid, and this is your extra oxygen, metachloroperbenzoic acid. Those are the 2 most common ways to do this. And the reason it's important is the first oxygen itself is, nucleophilic. However, with the second oxygen added, now you have a disproportionation of where the electrons are, and that second oxygen becomes electrophilic. And remember, our alkene is electron rich. So what we can do is we can get that reaction with that second oxygen, that electropositive oxygen, come in and interact with the alkene right here. And then notice we're forming a kind of a 5-member transition state here, because what's going to happen is these electrons are going to reach out and grab that hydrogen. The electrons that were on this hydrogen here are going to form the bond with that oxygen. The electrons of the alkene are going to form the other bond with oxygen. And then those last 2 electrons are just going to go back onto your species. And so what you end up with is, if you can follow where all those electrons went, okay, we have the electrons from the alkene here, the electrons from the lone pair here, the electrons from the hydrogen here, all forming this 3-membered ring. Okay? And then notice that when we have our other product here, It is just our regular acetic acid. We completely transfer that oxygen from one to the other. Okay, so this is an addition reaction to an alkene, and all we're doing is adding an oxygen across there. Okay, so it can add to either side. There's not really any specificity to that, but it will give you this epoxy formation. Okay, so the fact that it adds across the side, whatever your alkene was, maintains that stereochemistry because it's doing a single concerted addition and doesn't have time to rearrange. What this means is if your R groups were on the same side of your alkene, they're going to be on the same side of your epoxy. Okay. If they were on opposite sides of your alkene, they are going to be on opposite sides of your epoxy. So the stereochemistry of that double bond does not change when we do the addition across because it adds to one side and one side only. Okay. So the next addition reaction we have to this is to add hydrogen across it. Now, hydrogen's a nonpolar compound, and therefore it's not easy to add it across there. You could take hydrogen and alkene and heat it for days and almost nothing will happen. However, if you take hydrogen and adsorb it to the surface of a metal catalyst like palladium or platinum, in this case, we're using palladium right here, the hydrogen breaks that bond and bonds to the metal surface, okay? That makes that hydrogen now very active because it now has a polar bond between the metal and the hydrogen. Now, if your alkene kind of floats down and sets down on the surface of this, this catalyst surface, it will reach out and grab at one of these partially positive hydrogens and add it to your alkene. And then once it's added a little bit to the alkene, you can transfer another one and you end up with two hydrogens added across your double bond. Now, because you added it on that surface and it's contained on that surface the entire time the hydrogens are transferring, we get syn addition. Both of those hydrogens go on the same side of that double bond. Okay, do we see why that's syn addition? Because you're setting it down here, both of those hydrogens are transferred at the same time. Okay, all right. So in summary, every reaction we just did has a selectivity to it. And this is what you need to kind of get straight in your head, okay? In reactions that form carbocations, you get a mixture of syn and anti-addition, okay? So that would include the hydrohalogenation and the acid catalyzed hydration, okay? In the case of forming a metal salt, like the mercurization or the oxymercuration, we actually also have a mixture of syn and anti-addition. Okay. Now, reactions that kind of happen all at once, right, add across the double bond all at the same time, only add syn. Hydroboration, catalytic hydrogenation, and then we'll talk about syn dihydroxylation next, but that will also be there. And then reactions that only add anti are the ones that have that, actually this should be here, this adds anti. The ones that form those three-membered rings are the ones that are going to give us the halogenation is a anti-addition. But then if we had that three-membered ring and attack it with a hydroxide, we can get the halohydrin reaction as well. So this should actually be down here in anti-addition, sorry. Okay, questions on that? Okay, so the next thing we have to talk about is we have to talk about the oxidation states of carbon, okay? Because in our next things, we're going to do these oxidations where we're going to change the oxidation states of carbon by adding oxygens or subtracting hydrogens, okay? So in the case of organic oxidation states, we want to remember this little thing. It's Texas. There's a couple different ways to do this, but this is Texas, so I chose oil rig. Oxidation involves the loss of hydrogen or electrons. Oxidation involves loss of hydrogen or electrons. Okay, that's what oil stands for. Reduction involves gain of oxygen or electrons. Gain of hydrogens or electrons. Reduction involves gain of hydrogens or electrons. So if you're adding hydrogens to something, you're reducing it. If you're taking hydrogens away, you're oxidizing it, okay? So let's look at what that looks like on this side here. So the lowest oxidation state we can have is having as many hydrogens as possible on our system, okay? And to oxidize once, we're gonna add an oxygen, but notice we have one less hydrogen-carbon bond. So that means we've oxidized from going from an alkane to an alcohol. Now, if we lose one more hydrogen to create a carbonyl, we've oxidized it one more time because we've lost one more hydrogen and we have one more bond to an oxygen. We started with one bond to oxygen, now we have two. And then we can oxidize that even more to get us 3 bonds to oxygen and no bonds to hydrogen. And that's our highest oxidation state, the carboxylic acid. Okay. Now, if you have a disubstituted alkane, you can't go all the way to the carboxylic acid without very rigorous reagents. So our oxidation steps go from removing one hydrogen and adding one oxygen to give us an alcohol. Then by removing the next hydrogen, you can get to your carbonyl compound. So we have 2 bonds to oxygen, 0 bonds to hydrogen. Okay. And we'd have to do some rigorous oxidation to get this thing off here. So that's where secondary hydrogens will end up, usually at the ketone. Okay, so we're going to use this formal charge, this formal oxidation state to help us define a couple things about our reactions. Okay, so the way we calculate this oxidation state on carbon, now note it's not formal charge. This is oxidation state, so don't confuse the two. Oxidation state has everything to do with how many hydrogen bonds you have or how many oxygen bonds you have, okay? So in the case of hydrogens, you wanna subtract 1 point for each bond to hydrogen, okay? Carbon, bonds to carbon don't count. So that's 0, you don't add or subtract anything. However, any bond to a nitrogen, oxygen, or a halogen, or anything more electronegative than carbon, you get +1, okay? So oxygen, nitrogen, halogen is a +1. So if we look at the simplest one we have here, we have methane. We have a -1, a -1, a -1, a -1. So our oxidation state on carbon is -4, okay? Now, that's the lowest oxidation state we can have on carbon. In fact, as soon as you put another carbon on there, what's our oxidation state now? Okay, we have lost one of our minuses from that hydrogen. So now our oxidation state for this is actually -3. Okay, so that means methane is the lowest oxidation state we can have at -4. Okay, now let's take that example of that ethane and let's oxidize it a little bit more. Let's add an oxygen bond to that. So if we calculate that right here, and we calculate this side of the reaction here, we have 1, 2, 3 hydrogens. So those are all -1, which gives us an oxidation state of -3. But here we only have 1, 2. So we have -2, but we have an oxygen bond, so +1, which means our oxidation state is now -1. We went from -4 to -1 just by adding a carbon and an oxygen. Okay. So let's take that to an extreme. Let's go to carbon dioxide here, okay? Carbon dioxide has no hydrogens. It has no carbons. So that means each of these bonds to oxygen are a +1. So that means our oxidation state is 4. That's our highest oxidation state. It has 4 bonds to oxygen, okay? So our oxidation states can range from -4 to +4, okay? And one more try, let's do an aldehyde, because that's kind of halfway between an alcohol and a ketone. If we look at this one right here, we calculate just this carbon first. We have 1, 2, 3 minus, so that's a -3 oxidation state. This bond counts for 0. This bond counts for -1. This counts for +1 because there's 2 bonds to oxygen, making our formal charge a +1. So aldehydes have a +1 oxidation state. The alcohol, the primary alcohol, at a -1 oxidation state. A carboxylic acid is going to have a +3 oxidation state if it's bonded to a carbon, and a +4 oxidation state if it's not bonded to a carbon. Okay, so why is this important? Following the oxidation states actually gives us priority on one, nomenclature. Notice that the highest oxidation state is the carboxylic acid, which is also our highest priority. Aldehydes are next, ketones are right below, alcohols, etc. So oxidation state plays a role in nomenclature, but it also plays a role in can it be oxidized by an oxidizing agent, or can it be reduced by a reducing agent? If you're already at a lowest oxidation state, it probably is very hard to reduce. Okay, so now let's go back to reactions of alkenes with this new understanding of oxidation and reduction. And let's do what we call the creation of diols with oxidizers. In this case, we're using osmium tetroxide. And the cool thing about osmium tetroxide is it does a syn addition, and it gives the alcohols are going to be in the syn configuration because we have 4 oxygens on osmium here, and one of the oxygens is going to form a sigma bond with half the alkene. The electrons from the alkene are going to come out and bind to the next oxygen there to give us this cyclic osmate ester, okay? So this is the intermediate, okay? So this intermediate tells you exactly why both of those alcohols, one is going to be on each of those carbons of the alkene, and they're going to both be on the exact same side of that alkene. So we get that syn addition for alcohols that are 1,2. Alcohols that are 1,2 are called vicinal diols, okay, because they're next to each other. It's a 1,2 diol. Those are vicinal diols, okay. And then what we can see is as it goes from its original state at oxidation state of 8, it goes back to an oxidation state of 6. And then when it leaves, it actually ends up with an oxidation state of, it's cut off, but it ends up with an oxidation state of 4 because it transferred those oxygens off. Okay. So I'm on one more slide and then I'll let you go for the day here. I think it's one more slide. Okay. So because osmium tetroxide is number 1, very toxic, and number 2, very expensive, they've actually figured out a way to trick it. And so what they do is they use just a tiny amount of the osmium tetroxide, and then it'll do its addition to form our osmate ester here. And then as that osmate ester is hydrolyzed off by that sodium sulfate right there, it actually can be reoxidized by a compound, and the most one we call is the this one right here. It's an oxidized form of a heterocycle, and I can't remember the name right now. Oh, N-methylmorpholine and oxide. So we've actually take morpholine, which is a heterocycle, and we've oxidized the nitrogen, okay? Now that oxygen is very easy to transfer off, and so what it does is you can use this material to help oxidize off this to generate your osmium tetroxide again. And you get your vicinal diol, and you've regenerated your osmium tetroxide, so you can use trace amounts of osmium tetroxide and 2 equivalents of the oxidizing agent per equivalent of alkene. Okay? So, yeah, I want to do that one next. All right, questions on oxidation state. Remember, it's different than formal charge, oxidation state, and the use of osmium tetroxide. Do we see why it makes vicinal 1,2 diols? Do we see why it makes syn addition? Okay. Think about all those ones that are making that syn addition are forming, you know, they're adding across that double bond at the same time to give us that addition. And so we see that also. We saw that in hydrogenation. We saw that in the boronation. So we are looking at that same kind of addition, that syn addition. Okay, we're right here at 10:50. So I'm going to go ahead and stop recording. And if you want to stay back and, CHEM tutoring 1 to 3 today, flyer on Canvas. All right, if you want to stop and stay in